Thank you, Martina. Well, this talk is based on joint work with several co-authors. These include George Buzianis, Sebastian Jaibungo, and Leandro Sanchez Betancourt. And it's based on a paper which we put in the archive not too long ago, and you can find the details on this slide. Now, let me sort of set the scene by saying what the topic is. Pricing models driven by Lévy processes, of course, have been considered by many authors. What we're concerned with here is a broader, in fact, much broader family of models. These are the so-called Lévy-Ito models. The terminology, I think, is due to Mark Yor. So such models are driven both by Brownian motion and by Poisson random measure, where the Poisson random measure is taken to be associated with an underlying Lévy process. And this class of models is general enough to this.
Try okay.
Just one moment.
Magic touch.
Thank you. Okay. Yes, the class of models is general enough to include many of the familiar models, such as Lévy processes and Brownian motion models, but it allows one to create new models as well, and at the same time preserving a high degree of analytic tractability. Now, the need for systematic development of Lévy-Ito models, I think, is clear. Suppose that you are interested in Lévy models, and then you wanted to price a derivative, like maybe an option based on a Lévy model. Then the price process of the option won't itself be a Lévy process, but it will be a Lévy-Ito process. So in this sense, the category of Lévy-Ito processes has a nice kind of closure property. If you form a function of a Lévy-Ito process, and if it's sufficiently smooth, then this will be a Lévy-Ito process itself. I'll begin by just making a few background remarks. This will allow us to kind of logically develop the theory of Lévy-Ito processes. I think everybody knows what a Lévy process is. We fix a probability space and a measure, and then we're going to introduce a process which I'll call C, which has independent increments, and it's stationary increments, and there's continuity and probability, and then there's a Cadillac property. The key thing about Lévy-Ito processes is we have the Lévy-Khinchin formula, which then introduces a Lévy measure nu, which is kind of fundamental to the theory. And indeed, if we specify the Lévy measure and two constants, then this gets us back to the Lévy process. Now, what we're interested in is the category of processes that can be built up from these ingredients. So the next thing we need to know is the Lévy-Ito decomposition. So this shows that any Lévy process can be built up out of a Brownian motion and a constant and a Poisson random measure, where the Poisson random measure terms are divided into two parts. There's a part for small jumps and a part for large jumps. So there's some arbitrariness in where you draw the limit, and we'll take it to be at 1. So n denotes the Poisson random measure, and n tilde denotes the compensated Poisson random measure, where the Lévy measure is brought into play. So once we have these ingredients at our disposal, then we can define the general Lévy-Ito process. So we'll let y denote a typical such process. The first few terms are familiar from the theory of Ito processes. So alpha and beta are adapted processes adapted to the filtration, and But the gamma and delta processes are the extra ingredients. These are function-valued processes, if you like. They all depend on the jump size x. And again, there are two terms for the large jumps and the small jumps. And we require some conditions. The conditions on alpha and beta are the usual ones that one has from the Ito theory, but the condition for gamma is one that appears in the present context, and we'll call that the P2 condition, which we will impose in various contexts. Now, the next step is to note the version of Ito's lemma that crops up in connection with the Lévy-Ito processes. So we'll let y be, again, a typical Lévy-Ito process, and we'll write it in differential form. And then we can develop a kind of stochastic calculus generalizing the usual Ito calculus. And in particular, we have our gamma and our delta, alpha and beta. And if f is any function admitting a smooth second derivative, then we have a version of Ito's lemma, which is represented by this equation. So the first few terms are the familiar ones from the usual Ito calculus, and then the remaining three terms deal with the jumps. And at first sight, if you haven't seen such a formula before, it looks a little bit complicated, and you wonder how on earth can I deal with that. But in fact, it is perfectly manageable. It's more difficult than the standard Ito calculus, but it's just as useful as the Ito calculus, and it gives you essentially the way into dealing systematically with jump processes of the Lévy-Ito type. The key thing here is that if y is a Lévy-Ito process, then if you take a function f that admits a smooth second derivative, then f of y also gives you a Lévy-Ito process. So this is the sort of closure property that I was referring to earlier. And if you inspect the various terms in the Ito's lemma formula here, then you'll be able to identify the four alpha, beta, and gamma and delta processes that are the ingredients of the new Lévy-Ito process. So I'll mention a couple of examples. These are fairly standard and well-known examples, but the treatment that one sees in the literature tends to be of a rather ad hoc nature, so one can organize it a little bit more systematically. The first thing we need to consider is the stochastic exponential. So in this case, we have a problem of solving a certain type of stochastic differential equation, and so we have a capital gamma and a capital delta. They have to satisfy some conditions, and the idea is to solve the stochastic differential equation. Well, this can be solved completely by use of Ito's lemma and some standard manipulations reminiscent of the ones that you use in the usual Ito calculus. And we arrive at terms in the exponent, all of which can be expressed in terms of the original drift mu and the gamma and the delta process. So that solves the stochastic differential equation. Now notice in this case, for the small jumps, we have a compensated Poisson random measure, but for the large jumps, we don't. But we can put the problem in a slightly different way and develop martingales, and this is where the subject begins to become interesting and relevant to finance theory. So if we assume some extra conditions on capital delta, then we can introduce a compensated Poisson random measure in the stochastic differential equation for that term as well. And then this leads to the possibility of forming local martingales or even martingales. And indeed, after some manipulations and imposing the relevant conditions on capital delta, then we get an exact solution that is a local martingale, and with some further conditions takes the form of a true martingale. We can write the formula in various ways. I think perhaps what I've called equation 18 here is one of the more convenient ways of writing the result. And now the integration over the Lévy measure extends for all values of x. So with that in mind, then we can now turn to some finance theory. And the object here is to build up a kind of general model for a risky asset. And this can be done. I mean, there are various steps, but essentially what you want to do, assuming that the asset is non-dividend paying, is to impose the condition that the product of a pricing kernel times the value of the asset is a martingale. So first we introduce an interest rate in the standard sort of way. We require that it's predictable. And then we introduce a process lambda, which has the interpretation of risk aversion. And from that we construct a martingale, which I'll call M. And then the pricing kernel is taken to be of the form M divided by the money market account, B. So the pricing kernel is regarded as a sort of a given ingredient of the model. And the pricing kernel can be expressed in various ways, but the form expressed in 25 is perhaps the most convenient way forward. So we have our risk aversion process, little lambda, and then we have an interest rate, little r, and we have a pricing kernel. And next we impose the condition that the product of the asset price and the pricing kernel is going to be a martingale. Well, here we introduce another process, which I'll call capital lambda. Capital lambda is related in a very simple way to little lambda. So little lambda, you recall, is what I was calling risk aversion, whereas capital lambda has the interpretation of being market price of jump risk. And intuitively, for each value of x, lambda corresponds to the market price of risk per unit of intensity, where the intensity is the intensity of the Lévy measure associated with the underlying Lévy process. So if we're given an asset price S, and if it's strictly positive, then we require that the product of the pricing kernel and the asset price is a martingale. And after some work, and I won't go into the details here, but it's all in the paper, you can find a rather general expression for the value of a risky asset, non-dividend paying in a Lévy-Ito market. And this is the formula. Okay. The Brownian term I've simply suppressed because it won't fit on the slides. So tacitly, there are standard Brownian terms here as well. And they don't mix because the Brownian motion that you get according to the Lévy-Ito representation is independent of the Poisson random measure. So we have Brownian terms implicit throughout the discussion here, which I've simply suppressed for simplicity. Okay. Thanks for asking. Okay. If, on the other hand, you were to keep the Brownian terms and you were to suppress the Poisson random measure terms, then you would be back to more or less the standard market model for Brownian motion driven assets with general adapted volatility and market price of risk. Okay. So, so coming back to the general formula here, you'll see there's several different terms. First of all, you'll see the usual interest rate term, and then there's an excess rate of a term, capital R, which I'll come back to in a second. And then we have the volatility, which I'll call little sigma here. And then we have the market price of risk, lambda, and capital lambda, and the what I call the dynamic volatility, capital sigma. And you can see that the excess rate of return on the asset is in fact given by the integral of the dynamic volatility, sigma, and the market price of risk, capital lambda, with respect to the Lévy measure. So if you interpret capital sigma as being the riskiness associated with the asset, then capital lambda has the interpretation of being the market price of risk per unit of intensity, and you integrate over the jump variables. So in the end, in fact, one has a very nice formula for the general expression for an asset price in such a market. I'll make a few remarks. I mean, if we look at the sort of Ito form of the dynamics, then you'll see that the volatility that appears as the dynamic volatility, capital sigma, and the excess rate of return is given by the integral of the product of capital sigma and lambda with respect to the Lévy measure. Capital sigma is the risk in the sense that it determines the multiplicative factor by which the asset price jumps if the jump in the underlying Lévy process is given by the vector x. Finally, it's worth remarking that if little sigma is positive and if little lambda is positive, then this is a sufficient condition to ensure that the excess rate of return is going to be strictly positive. And in that case, the excess return is an increasing function, both of the level of the risk and the level of the risk aversion. So this is a sort of natural condition which carries over, in fact, from a simpler but similar result that holds in the Brownian case. So in short, the resulting framework is really quite intuitive.
Sorry, but is this sigma T of x deterministic or?
No, in the Lévy-Ito process, all of the coefficients are completely general predictable processes. Okay. So we're working at quite a high level of generality. Now, of course, you can make them deterministic, and that leads to interesting special cases, but that's a separate story. Those would then be specific models within the general framework. I'll conclude with a few remarks about interest rate models. Of course, there have been many interest rate models developed based on Lévy processes, and we have Ernst Eberlein in the audience, for example, who's a pioneer in that area. Here we're going to be looking at interest rate theory in the general Lévy-Ito setting. This, of course, includes the Lévy-based interest rate models as a special case. So the ingredients are a pricing kernel and a money market account and a system of discount bonds. The discount bond is defined in the standard way. So we can take our scheme for a single asset and apply it to each of the bonds. And then this gives us a set of dynamical equations for the various discount bonds. And you'll see that omega defines what you might call the volatility structure of the discount bond system as we vary the maturity date. So then we can apply our first result, and this allows us to write down the general form of the solution for a discount bond. And so you'll see the various terms here, the short rate, the excess rate of return, and then the volatility expressions for the small jumps and large jumps, and then finally the compensating term that we need. If you then take the limit as little t approaches big T, this gives you a formula for the money market account. And the reason for that, if I go back to the previous slide, you'll see the very first term on the left involves the integral of the short rate. So that's the money market account. And so if you simply set little t equal to big T by taking the limit, then that allows you to solve for the money market account. And then that in turn can be put back into the formula for the discount bonds. And then you solve, and this allows you to eliminate the short rate from the dynamics altogether and express a formula for the discount bond system in terms of the volatility structure and the market price of risk lambda and the initial term structure, which I'm calling P 0 little t big T, which is the forward price at time 0 for the purchase of a little t maturity discount bond a big T maturity discount bond at time little t. So this gives us essentially a complete expression for the value of a discount bond. So we don't really need to model the dynamics in our going forward. We can work directly with the formulae for the discount bond. So I'll make a few remarks. You see, once you impose the initial term structure and the market price of risk and the volatility structure, then the money market account, the short rate, the discount bond prices, the instantaneous forward rates are all determined. So essentially, this gives you a kind of a solution to the problem. Then to propose a specific interest rate model, then you need to choose a form for the market price of risk or the volatility structure. And this has to be sufficiently general to allow you to calibrate the model to whichever market prices that you feel that the model needs to calibrate to. And of course, this will depend on circumstances. For example, you might choose the volatility structure to be deterministic, and as Julian was sort of hinting at earlier, and then that leads you to a class of models which still has quite a bit of freedom in it that can be used for calibration. Well, the Lévy-Ito models have some advantages over the Ito models and the Brownian models. The chief advantage is really that they allow much more functional freedom for calibration in the Lévy-Ito case than they do in the pure Lévy models and the pure Brownian models. Many other aspects of interest rate theory can be developed in the Lévy-Ito context. I've mentioned one or two here. It's an interesting exercise to develop a Lévy-Ito-Vasicek type of model. This can be done, and it turns out to be completely tractable. And it has, in some sense, much more freedom in it than the standard Vasicek type of model, and yet it has the same degree of tractability. There are explicit formulae that you can develop for the bond prices and the initial term structure. Another interesting example are chaos-type models. Chaos-type models, which were originally developed in the Brownian case, can also be developed in the Lévy-Ito case. And so the Lévy-Ito family of processes admits a chaos representation of the Wiener-Ito type, much in the same way that Brownian motion does. So you probably know that Wiener invented the original Brownian motion chaos expansion, but then Ito developed the Lévy-Ito version of the chaos expansion, which of course is much more general, but it turns out rather miraculously, because it's not by any means automatic, so to speak, that the general Lévy-Ito type interest rate model can be represented by use of a chaos expansion, much in the same way that Brownian motion models can. One can also look at foreign exchange models. So these various special cases are all developed at length in the paper. And I'll remind you again where the paper is. Okay, thank you very much. Okay.
Thank you, Len. You're perfectly even in advance